Okay, let's look at the old exam. We'll go through some naming here. Our first one here, let's start off by numbering our chain. With these, we'll start with the carbonyl carbon. So we have 5 carbons in our chain. We have an alkene. So as an alkene, that would be a pentene. For the ester, we change the ending to 08. So we'll drop that E and add 08. This is a pentene 08. I must tell the position of the double bond. You don't have to tell the position of the ester because it has to be the number 1 position. The ester does. But we do need to know where that double bond is, the alkene. The alkene begins on carbon number 3. So you can put the 3 there in front, or you can put the 3 in front of the ene. Personally, I like it in front of the ene. That way there's no confusion. We have a substituent to take care of. We have a methyl coming off of carbon number 4. And then finally, whatever is coming off the oxygen, that what's on the oxygen in there, this comes from the alcohol. This is derived from the alcohol. The rest of this is derived from the carboxylic acid to make the ester. So whatever is on the oxygen goes out in the very, very front of everything as a separate word. We have an ethyl group that goes out in the very front as a separate word. That's telling me that's what's on the oxygen. There must be a space right there. You must have that space, so that there's no confusion as to what's on the oxygen. It's that separate word. Questions on that? Now this alkene does not have the possibility of an E or Z. If it did, then you would need to put that on there as well. But there is no E or Z possibilities because you can't assign priorities on this carbon. It's got 2 methyls, 2 of the same thing there, and you can't assign a priority there. So there is no E or Z possibilities on that one. Okay, let's name our next one here. Again, we're going to number our chain. We're going to start with the carbonyl. We've got 3 carbons in our chain. Now you might say, I went 1, 2, 3. Why didn't I go 1, 2, 3? I got a tie both ways. You choose the one with the most substituents. So we're going to go this way. That will give us the most substituents on our chain. 3 carbons there as the chain. That is a propane as an alkane. We change our ending to the, drop the E and add amide. It's a propane amide, since we have the nitrogen with the carbonyl. We have our substituents to put on. Let's see what we have. We have a phenyl group, we have a methyl group, we have another methyl group, and an ethyl. Maybe we should just write things down here. Let's see. We've got a methyl on the nitrogen. We've got an ethyl on the nitrogen. We've got a methyl on carbon number 2. And I have a phenyl on carbon number 3. Now that's going to go out in front in alphabetical order. So alphabetically, ethyl comes first. So we have N-ethyl. Methyl comes next, and there's 2 of them. We'll list this as an N2. You must tell the position of both of them. One's on the nitrogen, one's on the 2 position. We list the letter first. So this is an N2 dimethyl. and then finally the phenyl. So this is an N-ethyl, N2-dimethyl-3-phenyl propane amide. Questions? Okay, our next one here, we have an aldehyde, and we have the aldehyde group is on a ring, directly attached to a ring. Now, if you recall, what we talked about with those is you name the ring and then add the suffix carbonyl. Our ring is a cyclohexane. So we name the ring and then add carbonyl, only when the aldehyde group is directly attached to the ring. This is cyclohexane carbonyl. Now, we have a nitro group as well, and I need to know the position of that nitro group. Our aldehyde, let's number our ring, where the carbon on the ring that has the aldehyde group gets the number 1 position. That aldehyde has a higher priority than the substituents. So our nitro is on carbon number 4. This is 4-nitrocyclohexane. Now, noticing the stereochemistry of the ring there that's shown, we have the nitro group is on top, and we have a hydrogen that would be pointing down. Nitro's in the equatorial, hydrogen there's in the axial, so hydrogen's going to point down. Over here, the aldehyde's in the equatorial, and the hydrogen would point up here. It's in the axial and it points up. Remember, those axials point the direction the ring is pointing. So the ring's pointing downward here, hydrogen points down. Ring's pointing up, hydrogen would point up here. So I have a nitro on top, hydrogen on bottom. Here on this side, hydrogen is on the top and the aldehyde's on the bottom. So the two substituents, the two groups, they're on opposite sides. You got one on top, one on bottom. They're on opposite sides. That's trans. Trans is the stereochemistry there. They're on opposite sides of the ring. Questions? Now that's how we deal with an aldehyde directly attached to a ring. Any other aldehyde, something like this, where it's in a chain, we just simply number the chain. Whoop, 4. 4 carbons as an alkane is butane. And we change our ending, we drop the E, and we add Al to represent the aldehyde. This is a butanal. You don't have to tell the position here. It has to be the number 1 carbon. And so for a chain, we use an Al ending. When we have an aldehyde directly attached to the ring, we use carbonyl. So that was a difference. Questions? Our next one here, we have a nitrile. That nitrile carbon gets the number 1 position. And we number on out, 2, 3, 4, 5. 5 carbons in the chain is a pentane. And we simply add the suffix nitrile. This is pentane nitrile. Takes care of our nitrile. Then we have a substituent to take care of. On the number 5 carbon, is a cyclopentyl group. Remember, our groups end in YL, so that's a cyclopentyl. And that's on the number 5 carbon, so don't forget that. So a 5-cyclopentyl pentane nitrile. Questions? Now be careful, I get students all the time, they go along numbering and they want to make this number 6. No, you're numbering the chain. That carbon's part of the ring. You're dealing with that right here. That's a cyclopentyl group. That is taking care of that carbon there. That's not the number 6 position. That ring is on number 5. You're numbering the chain. You're not numbering that ring here. Questions? Okay, the next one on the old exam is a mechanism question. And it is dealing with a Wittig reaction. Let's go through and draw the full mechanism on how we get from those starting materials to this product. Now the anion here is acting on our ylide, is acting as the nucleophile. So this is our ylide that attacks the carbonyl carbon because there's partial positive charge on all carbonyl carbons. And we kick the electrons up onto the oxygen. Now we've got an oxygen with a full negative. We have a phosphorus with a full positive. That oxygen is going to give a pair of electrons to the phosphorus. That negative charge is attracted to the positive charge. Now we temporarily form a little 4-membered ring. We know 4-membered rings aren't very stable. So this will break apart. And we're going to break apart in a different way than it formed. We could go back the other direction. These could reverse and go back, but then they'll just add right back. So if you look at what we formed, we just formed this bond, and then we formed the phosphorus-oxygen bond. So these are the 2 bonds that we just formed. So we're going to break the other 2 bonds. So let's break the other 2 that are in the ring. And that will lead you to the product. That will give us the alkene there. And then as a byproduct, you get the phosphine oxide as a byproduct. And we have made the alkene. Questions? So there's the full mechanism, all the curved arrows. So our next question, we're looking at, says give the major products for the following reactions. First step, we're reacting with potassium cyanide. That is going to be a nucleophile. Let's see what we have over here. So I've got potassium cyanide reacting. Over here we have a secondary alkyl halide. Secondary alkyl halides do SN2 with weak bases, they do E2 with strong bases. The cyanide is a weak base. That's not one of our strong bases. It has resonance, which weakens it. So that's a weak base. So we're going to do an SN2 substitution. Now the question did say show stereochemistry on this, so we need to make certain we show our stereochemistry. Remember, SN2 does backside attack with inversion of configuration. So that nitrile group that we're putting on is going to come in from behind, and it will be a dash. That's the backside attack. The chlorine with the wedge, this is now going to be a dash. That's our inversion of configuration. So there's our SN2 product after the first step. And I did review that, so that's fair game. Anything I review is fair game. So if you look back in your notes, yes, I talked about this when we did hydrolysis of nitriles. We went through several different nitrile compounds, and I did review the SN2, so that's fair game. Okay, so second step, we've got acid, water, and heat. That will hydrolyze the nitrile to a carboxylic acid. I'm not going to go through all that mechanism. You can look in your notes. I told you I will not ask that mechanism on the exam. It's very lengthy. Now, as far as the stereochemistry, everything stays the same. That nitrile is hydrolyzed to a carboxylic acid, but we retain our stereochemistry because nothing attacked this carbon. Back here we attacked this carbon, we had the inversion configuration. But here with the hydrolysis, everything's taking place on the nitrile. We first protonate the nitrogen, and then the water attacks the nitrile carbon, and everything's happening right there. So we're not changing that stereochemistry. Nothing attacks that carbon. It stays the same. Okay, so there's our final product on that. Questions?
Give it an internal number now.
No. SN2 is stereospecific. SN2, you only get backside attack. So this is the only product that you get. If it had been an SN1, then yes, you would have enantiomers. But with an SN2, they are stereospecific. You only get the one enantiomer. You don't get the other. You don't get a racemic mixture like you do with SN1. So this is the only product. Other questions? That was a good question. Okay, let's take a look at the next one. First step, we have ozone, so we're going to make the ozonide. Second step, the dimethyl sulfide breaks the ozonide apart. So these two steps go together. These two steps are cleaving that double bond. This will give us the ketone. Cleave that, the other side, the top side, winds up making formaldehyde. We're not concerned with that. We're looking at the main big organic molecule. So we've made the ketone right there. Third step, we're reacting with the diol and acid as a catalyst. This diol, if you recall, that that is a protecting group for carbonyls. So this is making the cyclic acetal. The acid was protonate to carbonyl, and then the alcohol attacks. We have made a cyclic acetal. We have put a protecting group on that carbonyl. Now, remember that our protecting group here, making these cyclic acetals, this only works for aldehydes and ketones. This will not react with an ester or a carboxylic acid or an amide or something like that. This only works for aldehydes and ketones.
Would it work if you had
No, they're not going to do. They're not going to make the cyclic acetal with any of the others. You can get them to react. If I had heat, and I can get them to do something, but they're not going to make a cyclic acetal. So, aldehydes and ketones only for the cyclic acetal. We're not going to talk about any of those other reactions.
Does it prefer one over the other?
Aldehyde's more reactive, yes. So you can, if you're careful with it, you can selectively protect an aldehyde over the ketone. Aldehydes are always more reactive than a ketone because of sterics. But I'm not going to do that to you. Now, I will have maybe a ketone and an ester and expect you to know, hey, the ketone reacts and the ester does not. But I won't put an aldehyde and a ketone both in there.
Then why did it react with the ketone over the formaldehyde that we made in that reaction?
We can drive the aldehyde off. You can. So you mean for this to be purified. You know, after I do this step, I'll purify and then react with the diol. So yeah, we get rid of that. That's a little small compound. You can just boil that away. No problem. You just heat a little bit and boil that away. Now, most of our examples, I did have somebody come and ask me about this, one of the homework questions. The examples I did in class, the cyclic acetals that we made had 2 carbons here for the diol. You can also do 3 carbons. You can do 3 carbons. If I had done the 3 carbons with an acid as a catalyst, let's just look at that real quick. It still makes a cyclic acetal. Instead of a 5-membered ring, you have a 6-membered ring. No different. It's still made, that's still a protecting group, still works. It's just got 1 more extra carbon. Now you don't want anything more than that, because anything more than that, you get, that's too big of a ring size. 5 and 6 membered rings are our most stable rings. You always like 5 and 6 membered, those are good. And you can always have other things attached to those carbons. I've got 2 carbons between the alcohol here. Here I've got 3, but you could have other things attached. So instead of these being, 2 CH2 groups, I could have done, say, here. I could have done that diol with an acid as a catalyst. That's still a diol. That's still going to make it a cyclic acetal right there. I ran out of room there. Sorry. I think you can see it there. So you have that ring right there is that top one. there's my two oxygens from the diol. There's those two oxygens. And those two alcohols attacked the carbonyl and got rid of that.
You can't see it on the camera.
I'm sorry?
You can't see it on the camera. The answer.
Well, good enough for them. They didn't come. Yeah, it's showing up. Got the little record there in the way, but it's catching it. Any questions on that? So there's other diols. What I want to point out, there's other diols that will work. They had several in the homework that I had in the textbook that had other diols, and I had several students stop by and ask me about some of those. They're like, "What's going on here?" I'm like, "It still works the same. It's still a diol. It doesn't have to be the one example I did in class. You can have other diols will work just the same." Let's see here. Our next one here, we are reacting this ketone with MCPBA. This is the Bayer-Villiger oxidation that we're doing. There was supposed, I guess that's a little bit of a mistake there, slight mistake. There was supposed to be an acid catalyst with that. And I didn't have it on there, but you knew what I was meaning. We're supposed to have an acid catalyst with that. Okay, so the MCPBA, that's a peroxy acid. Any peroxy acid will work, but MCPBA is the most commonly used. So that's the one everybody uses, so that's what I'm going to use. You can use any peroxy acid, but MCPBA is the best, so why not use the best every time? That's the one everybody uses. Now, so the Bayer-Villiger oxidation makes an ester out of the ketone. If you use an aldehyde, it's going to make a carboxylic acid. So we went through the mechanism on this. You have a migration step. So after the peroxy acid reacts, then you have one of these two sides is going to migrate to the oxygen. And so we talked about the migration order. We said the first to migrate is a hydrogen, if you have a hydrogen. So that would be where we started with an aldehyde. If we're doing an aldehyde, it's the hydrogen that migrates, and so you're always going to get a carboxylic acid if you have an aldehyde and use MCPBA. But with any of the ketones, then you really got to start looking at the carbons on both sides. Phenols migrate before anything else, any other carbon group. And then we have the tertiary alkyl, secondary alkyl, primary alkyl, and last is a methyl group. So looking at this example here, we have a phenyl group, we have a secondary alkyl, so the phenyl is going to go first. Phenyl is going to migrate first. So that's the order here. The phenyl side is going to get the oxygen. That's the side that winds up with the oxygen. The phenyl migrates to the oxygen, and you wind up, that's the ester you wind up with. So you need to know that migration order. Questions? Yes?
If the cyclophenol had a methyl on it, would it go to the more substituted side?
If the
like where the carbonyl carbon is attached to the cyclophenol, if there was a
So
methyl.
methyl there,
Right. Would that make it more, the oxygen go to that side? Because
this one here is still phenyl would go first. Phenyl beat out all those other carbons. This is a tertiary alkyl. So if you look, coming off the carbonyl, you've got carbon, 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 and so that's counted as a tertiary carbonyl. Phenyl still goes before the tertiary carbonyl. Now if I had that one and say an unsubstituted one on this side, then you got tertiary versus secondary. This side would go, and so we first, and you wind up with the oxygen on that side. So there's your product. But the phenyl beats any carbon group. The only thing that migrates before the phenyl was the hydrogen. Other questions? Okay, looking at our next one here. Let's just take it step by step. First step, we have hot potassium permanganate. That is going to oxidize the benzylic carbon. It will cleave off anything out past that. And we make the carboxylate ion after the first step. Second step, we're acidifying, so that's where we pick up the proton. You can't make a carboxylic acid in a basic solution, so you have to acidify in a separate step. So this gives us the carboxylic acid. We have oxidized that benzylic carbon to a carboxylic acid. Step 3, we are reacting with PCl3. We also talked about we can use PCl5 or we can use thionyl chloride, SOCl2. That's thionyl chloride. Any of the three will convert a carboxylic acid into an acyl chloride. So there's our product after the third step. Fourth step, we are reacting with the dibol H. Now we talked about two new reducing reagents. We had the dibol H, and then we had the tri-T-butoxy aluminum hydride. Tri-butoxy. So that was this one. And the lithium tri-butoxy aluminum hydride. So either one of these can be used to reduce that. Dibol H is just easier to write out. Now, if you recall, dibol H looks like this. This was dibol H. This is what it looked like. So we're transferring a hydride in to the carbonyl. We kick the electrons up onto the oxygen. They kick back in, reform the carbonyl, and kick the chlorine off. So this can reduce that acyl chloride to an aldehyde and stop at the aldehyde. Now we said we could do this with acyl chlorides. We could also use the dibol H or the tri-butoxy aluminum hydride. We could also do that with esters and still stop at an aldehyde, or we can do nitriles. Take a nitrile and reduce it to an aldehyde and stop. So we can reduce any of these three to the aldehyde stage and stop there at the aldehyde. Questions?
I actually do have a question.
Okay.
It's a really dumb one. With the hot potassium permanganate, does it have to be a carbonyl group, or can it just be a basic carbon in the benzoic position?
Just any carbon, any benzylic carbon. Any benzylic carbon can be oxidized to the carboxylic acid. So we talked about a lot of different ways to make carboxylic acids. We went through, there's like 6 different ways that we went through. But yes, the hot Carbonyl 4 will oxidize any benzylic carbon to a carboxylic acid group.
I thought so, I just wanted to confirm.
Yep. I get to roast the wrong one, didn't I? We just did 3D. Okay, our next one here we have sodium cyanide and hydrochloric acid. Sodium cyanide with an acid. This will make hydrogen cyanide. That's what's the reacting reagent. We talked about we normally make this in situ, so we make the hydrogen cyanide in the same flask as what we're going to react with, because hydrogen cyanide is a gas, a poisonous gas, and so you don't want to have to deal with that. So we make it in the same flask as what we want to react it with. Now let's examine what we have over here. We have a ketone, we have an ester, and we have an amine. Hydrogen cyanide reacted with aldehydes and ketones. You can also think about it, aldehydes and ketones are more reactive than an ester. So of the carbonyls, aldehydes are the most reactive of the carbonyls, and then the ketones, and then an ester, and then a carboxylic acid. We also included acyl compounds in there, talking about reactivity of things. And so we dealt with that with some reactions. But as far as these go, it's the ketone that's reacting. The ester's busy doing resonance. And you typically need heat to get esters to react, because they're busy doing resonance. They don't want to do anything. They're already busy doing something else. You got resonance going back and forth, back and forth. So it's that ketone that's going to react. We're going to protonate the carbonyl. That makes it more susceptible to nucleophilic attack. So the cyanide can attack and kick the electrons up onto the oxygen. And we make a cyanohydrin. this is a cyanohydrin. Now, if you recall, a cyanohydrin has a nitrile and an OH attached to the same carbon. That is a cyanohydrin. So we make those by reacting hydrogen cyanide with aldehydes and ketones. Questions on that? Okay, first step, we have a diol that we're reacting. We have an acid in there as a catalyst. This is going to make that cyclic acetal. That's our protecting group. Now we have a ketone, and we have an ester. We're going to protect the ketone. This only works with aldehydes and ketones. Okay, so we now have protected that ketone. Second step, we're reacting with a reducing reagent. Okay, so that's the other reducing reagent. We did the dibol H just a moment ago. This is the other one. There was the two. You could also use dibol H here. So that will reduce the ester to an aldehyde and stop at the aldehyde. So we transfer a hydride in, we kick the electrons up. Those electrons are going to kick back in and reform carbonyl, and we'll kick the oxygen off, so those electrons kick back in, reform the carbonyl. That's going to make the aldehyde, and kick this oxygen off. Now that's a cyclic ester, so that oxygen is still attached back on the back side. Still attached back over here. He left off, but it's still attached on the other side. But we've made the aldehyde. Now, last step, we're adding in acid and water. One, that acid is going to protonate that oxygen that's got the negative charge, but acid and water also removes our protecting group. So we get our ketone back. Remove the protecting group, we get the ketone back, protonated that oxygen, so I have the alcohol, and of course the reducing reagent made the aldehyde there earlier. So there's our final product. So we protected that ketone so that it didn't react. Otherwise, the reducing reagent would have went to the ketone first because they're more reactive than an ester. So it would have went there first. So we protected the ketone so that this had no option as to where to react. Now, we did talk about other reducing reagents. We could have used, you could have used Dibol H, we'd got the same product. If we'd had LAH here, then you wouldn't have stopped at the aldehyde. That would have got further reduced all the way to the alcohol. So if we had had LAH right there, this would have been an alcohol, and we would have had an alcohol here. But with the lithium tributoxy aluminum hydride or the Dibol H, it stops at that aldehyde stage.
Question.
Yes.
So you said what removes the protecting group?
I'm sorry?
What removes the protecting group? You said water and something?
Water and acid. Water and acid takes the protecting group off. Which water and acid usually is written as a hydronium. But water and acid removes that protecting group. Other questions? Let's see what we're doing here next. Let's see, we got a primary amine that we're starting with. We have a primary amine. And we have an aldehyde. Now we happen to have two equivalents of the amine, and I've got two aldehydes. We know a primary amine and an aldehyde will make the imine with an I. If you use a secondary amine, you make the enamine. But with a primary amine, you're going to make the imine with an I. Let's just go through this. So, the acid catalyst, I'm just going to redraw it up here. It's going to protonate one of those carbonyls. That's making it more susceptible to nucleophilic attack. The amine is going to attack, and kick the electrons up. I told you, let's see. I don't remember if I told you whether I would ask this one or not as a mechanism. This one's pretty straightforward, it's not too bad. Now, we're going to move a hydrogen over so that we have a water molecule that can leave. Now I've got lone pair back on the nitrogen. I have a water molecule that can leave. That's going to kick in to form the double bond and kick off the water molecule. There's a plus charge back on the nitrogen. We just need to get rid of that extra hydrogen and we'll have the imine. We just kicked off water. Water can grab that extra hydrogen. So we've made, right here, we've made an imine. Now, I still have an aldehyde. I had two equivalents of the amine, so the same thing is going to happen over here. We got our acid back. Water grabbed the proton, so you got acid back. It is acid catalyzed, so we can do all of this again on the other carbonyl.
Where did the second phenyl ring come from?
I'm sorry, I got carried away, didn't I? Sorry about that. Why didn't you tell me earlier?
I thought I was just dumb. I was just going to go with it.
I didn't want to interrupt you.
Sorry about that. That's a hydrogen there. I carried it all the way through it.
Hey, consistency is key.
Yeah. Once I go to the trouble to put it on there, I'm not going to take it back off. Okay, there we go. So now, sorry about that. Now the same thing will happen on the other aldehyde. I thought something looked weird when I was looking at it. So you wind up making a di-imine. There's our final product. We've made a di-imine.
And the imine is just a nitrogen bond.
Nitrogen with a double bond is an imine. Now, we make the imine with primary amines and an aldehyde or a ketone. You make the enamine if you use a secondary amine. So if I have a secondary amine here, secondary amines with an aldehyde or ketone make the enamine. And an enamine has a double bond, has a nitrogen on a carbon-carbon double bond. The imine, the nitrogen is involved in the double bond. You have the double bond on the nitrogen. Here you have a nitrogen on a carbon-carbon double bond. That's an enamine. So you have that when you use a secondary amine. Now, we do this in my research lab. I don't know if any of you know her, Netta, that does research for me. She's working on making di-imines. Megan in my group is also going to be making di-imines with her compounds as well, just a different one. So this is, while I've got this up here and mentioned that, this is a little bit of knowledge that you need to know about. Especially if you go on to graduate school in chemistry, make certain you're going to be taking, first year you take all these classes and you're done with classes after your first year in grad school. You just usually have 1 year classes. Sometimes you might have a couple classes your second year, but usually you get the majority of them done your first year. Other things that you have to do if you're working on like a PhD in chemistry, you'll have cumulative exams that you have to take and things like that. And you want to make certain you know what kind of research your professors are doing, because they will often ask stuff about their research because that's what they know the best. That's what they're experts in. So make certain you know what kind of research they're doing. Know a little bit about their research. And it will benefit you greatly. At some point, you're going to come across similar reactions and things. Because, like I said, that's what they know the best, and that's what they will often test on. So that's what I did that particular year. So in 2018, I think that's when I first decided. That's when Netta first joined the group, and that's when I first thought about these di-imines. I was trying to design something for her, and I came up with this idea that that's what we're going to make. And so I asked it on the exam that year. So just a little side note there. Okay, so we've went through, let's see, we got through 3 pages here. So, and I've been going almost an hour, and my battery only lasts an hour. So let's take about a 5-minute break. I'll switch out battery, and then we'll film part 2 here.